All right, so chapter 34 is about images. So we're going to learn how images are formed by mirrors. A mirror comes with different kinds of mirror. You have the plane mirror, you have the mirror with the curvature, and also how the images are formed by a thin lens or a combination of lenses and the applications of this optics. All right, so let's start from the basic plane mirrors. I'd say you have a mirror and you actually use mirror. Hopefully, everyone, you look at yourself in the mirror, and the mirror usually, is a plane mirror, meaning that it's flat. So this is how images are formed. So this is the mirror, and a lot of time is made of glass, and behind the glass is a coating, and the coating is where the image will be formed that you can see, and this is the object. So this is so the O here indicate the object, and the P here indicate the object distance. So you can see that because when you have the object, basically it is a source, it's a light source. So you have the light that's coming out of you, coming out of this object and striking the surface. And because this being light ray, it has to follow the law of reflection. So it's going to reflect it off the surface. And so you can see that if we follow do a ray tracing, let's start from the middle one. So the middle one, you have a light that's incident perpendicular to the surface, because there's no angle, so the angle is 90, so it's going to reflecting off the surface without any deviation. Okay, and we can follow another the second line ray, let's say this one. So you have a light that's coming at this angle, and the dashed line here, the horizontal dashed line indicate the normal. So we know that it has to be the reflected ray has to be symmetrical about the normal. So you have the incident ray, reflected ray, have another one, incident reflected, incident reflected, incident reflected. So you can see that all this reflected ray, they do not converge on this side. Okay, so where's the image? So in order to find the image, instead of using the finding the image in front of the mirror, you would do the you would draw the extension lines of the reflected ray. So this one extension line is here, this one extending line is here, and you can see that they all converge, they all intersect at this point, and this point is where the image is formed. And so this is I, the image distance, and this is P, the object distance. So by convention, the object distance is placed to the left of the object. So P is in front of a lens or mirror is considered positive. There might be situations that the object is actually behind the lens or mirror, then that will be considered negative. If it's in front, that's positive. Behind, that's negative. Now for image, if the image is behind a mirror, then that is not real. It's what we call virtual, and the sign is negative. Okay, so signs are very important when we talk about how images are formed, because the sign tells you whether that image is real or virtual. If the sign is positive, then it is a real image. They are formed by real light rays. If the sign is negative, then it indicates that the image is virtual. It is formed by virtual light rays. Okay, so in other words, you can see this one. It is this is a one-on-one correspondence. You have the object in front of a mirror, plane mirror, and you're going to find the image. That's exactly the same distance, but it's behind the mirror and it's formed by virtual light rays. So so your I here will be negative. That's why we have I that's equal to negative P. And so this is the closer level of the light ray. And as you can see, the incoming, the outgoing, and then extension. And this is incident, so there's no deviation. And then this produce the image. Okay. What about when you have the extending object? When you have an extending object, let's look at the light ray. So the top one is vertically incident on the surface. So the return light ray is going here, and then draw the extension. Okay, so this is the tip, this is the tip, and then the tip here, and then you go from here, there's a reflection. So you have that, so you can see that this is still the tip, and here, and you go here. So you can see that when you have the other plane mirror, it produces an image that is virtual because it's virtual light ray, and has the same image, has the same distance and same height, okay, and same orientation, okay. So this is this is how they we have a plane mirror, and it's produced by image produced by the plane mirror. What about when you have a curved mirror? So when you have when you have the a section of the mirror that is cut off the a circle. So this is, and this is this is the reflecting surface, and the and so you have the object in front of a spherical mirror, and we want to see how the image are formed. Again, it has to follow the law of reflection. Here are a few things, quantity that you need to be aware of. So the object is placed that distance p here. So that's the object distance, and this r is the radius of this sphere. So and this is what we call the central axis, and c is the center of the curvature. So you have the object placed in front of a spherical mirror, and this is a concave mirror. So when you have a concave mirror, and so you have a light ray that's incident on the surface, and there's a normal that did not draw, but basically it's perpendicular to the surface. So and the reflected ray has to be symmetrical about the normal. So you have one reflected ray, you have another one coming and reflected off. As you can see, these two do not converge on this side. So again, you have to draw the extension of the reflected ray to find where the image is formed. And this is where the image is formed. So you can see that this image is, because it's produced by virtual light ray. So this image distance, your eye here is negative, and it has a, so it's a virtual image, and it is actually larger than the original. So we know that it is enlarged, and also it has the same orientation, and it's on the other side where the object is. Okay, so this is the property of this image formed by concave mirror. And for concave mirror, how do we find the focal length? What we can do is that we can send parallel light rays, and then in front of the concave mirror, and see where they converge. And what we found is that when you have a light ray parallel to the axis going to be reflected off, this is going to be incident and reflected off. And we found that they converge at this point. So this point is what we call the focal point, okay? And this distance is what we call the focal length. And several things to be noted. One is that you can see that this focal length is real because it is formed by the real light ray. So the focal length is positive. In addition to that, for concave mirror, your R is positive. So again, when you're dealing with the lens or mirrors or images, the radius has a sign, focal length also has a sign. And so we found that the focal length is just half the radius, okay? And because because R is positive, your F also is positive for concave mirror. Now we can have another mirror that is what we call the convex mirror. So convex mirror is is like this. So it's convex, and you have an object. So again, you have an object in front of a mirror. That's where the images are formed. The images are formed. So you have the one light ray that's coming here, reflected off, coming, reflected off, and this two far away. So you have to draw the extension line. You find that the images are formed, behind, on the other side where the object is, and it is upright, and it is virtual because it's formed by virtual light ray, and it is actually smaller. So you can see that the size of the object will be different when you're dealing with a spherical mirror. Okay, and let's look at the focal length. So light ray parallel, and then reflected off, parallel, reflected off. These two reflected ray will not converge on this side, but it will converge on this side. When they converge on this side, and this is where the focal length is, and it is a virtual focal length and the virtual focus. So so again, it follows this, And because your R is negative for convex mirror, so your F is also negative. So when you do problems, make sure that, first of all, noting, which mirror you're dealing with, whether it's concave or convex, because, with the concave, your R and F are positive. With convex mirror, your R and F are both negative, okay? Right, so the next thing is, so how do we find the, the previous slide tells you some of the how the images are formed, and we can have, we can go, is it, sorry, okay, so we can go a little bit further, in general, for spherical mirror, this is the equation that you use to calculate where the images form, and several things to be noted. I is positive for real image, and it is negative for a virtual image. And for your P, that's also the same. If it's in front of a lens or mirror, it is positive. It is behind the lens or a mirror, then that's negative. Okay, and F, of course, concave mirror is positive, convex mirror is negative. And so here are a few additional diagrams to show you how the images are formed. So if you place, so for concave mirror, if you have an object that's placed in, within the focal length, so you can see that this is one light ray coming reflected. These two do not converge, and you draw the extension line, it is converged here. So you can see that when the object is placed in, within the focal length, it's going to produce a virtual image. It's going to produce an enlarged virtual image and has the same orientation as the object, and has to be on the other side where the object is, because that's where the virtual is formed. Okay. Now we could have you could have the if you place the object directly at the focal point, you place that directly at the focal point. So this is the incident light ray reflected, and you'll find that these two are parallel to each other. And when they're parallel to each other, then you draw the line, you'll find that the image cannot be found because it will be to the infinity. And just based on this equation, that's also can be, you can see that, because when your P is equal to F, then these two cancel. So your I, so your 1 over I is equal to 0. I has to be either positive or infinity. It will be infinity. So no image will be formed when you have the object placed directly at the focal point. Now, what about if I have an object that is placed outside the focal point? So if you do that, let's say when you have an object, the incident light ray reflected, and you'll find that when you have an object that's placed outside the focal point, it's going to produce a real image, because this image is formed by real light ray. In addition to that, you can see that it is actually flipped. The image is actually on the opposite, is actually flipped, and also there has to be on the same side in order for the real image to be formed. So again, if you use this equation, that would tell you that your I, when you do this scenario, your I will be a positive value. Okay, and so these are the things to describe the image, whether it's real or virtual, whether it's enlarged or shrunk, or whether it is on the same side where the object is or not, or whether it's upright, same orientation, or flipped, with respect to the original objects. And here's another equation that we use a lot, the magnification, which we call a lateral magnification. There are two ways to do that. One is the height, the image height over the object height. Okay, and we use the absolute value because your M, the magnification, also comes with a sign, and that sign tells you whether the image is flipped or not flipped. Okay, but then when you use the object height, you do not have that information, whether it's same orientation or flipped. However, if you use this expression, which I couldn't see here, but let me rewrite it here. So you have the M that's equal to negative over I over P, because I, image distance, has a sign, P also has a sign. So when you apply this equation, that will tell you whether M is it is positive or negative. If it is positive, it means that it has a center rotation. If it is negative, then it means that it is flipped. Say, for example, for this one, the image distance is positive and the object distance is positive. So when you do the I over P and then there's a negative, your M is negative. So for this one, your M is negative. So we know that the image is actually flipped. Okay, and then let's take for this one. So this one, your P is positive and your I is negative. So you have negative, negative, and so your M here will be positive. If it's positive, it means that it remains the same orientation. Okay, so that's how you apply this equation and that equation in order to determine the attributes of the image, whether it's larger, whether it's this is the equation to determine whether it's larger or smaller, and this is the equation to determine whether it's flipped or same orientation, and this is the equation that tells you whether the image is whether it's virtual or real. Okay, right. So here are a few more diagram to show you how the images are formed. So you have a concave mirror, you have an object that's outside the focal points, and just we know previously that it's going to produce a real image, and it's going to be inverted on the same side where the object is. So you can see that parallel light ray, it will go to focal point. If it's go through a focal point, reflected ray has to be parallel. So just by using this true light ray, you'll be able to determine the image, and you can see that is smaller, inverted, real on the same side where the object is. Okay. Now we can have an object, and there's two additional light ray that you can use to determine where the image is formed. One is that you send a light ray and go through the vertex of the sphere, reflect it off, and it has to be symmetrical about the central axis. So that's one light ray. And then another one is when you have the light ray that goes through the center of curvature, there's no deviation. And so, and then when you look at this two reflected ray, this is where these two are intersecting. So this is where the image is formed. And you can see that it is, it is real, it is inverted, okay? Meaning that your M is negative and your I is positive, okay? So these are the four light rays that can be used to determine where the image can be formed. Parallel, focal point, parallel. Vertex, symmetrical, center of curvature, no deviation, okay? Same light ray can be applied when you're dealing with a convex mirror. So you can see that this is where the object is. If it's parallel, then it has to, reflect, it has to go through the focal point. It will go through this focal point. And then if this is parallel, then the reflected ray has to go through anyway. So this is where the image is formed. This is a little bit messy. So the first one, let's say the first one is coming from the focal point. So as if coming from the focal point. So if you draw like this, then this is parallel reflected, and this is like coming from the focal point, then then the reflected will be parallel. And then when you draw the extension line, this is where the image is formed. And so this is equivalent to this two. And then for this two, you have the one that's if this coming out of the focal, if this is incident and the extension line go through the center of curvature, the reflected there will be no deviation. Or the one that's that is coming at the vertex, then symmetrical. And then you draw the extension line, then it is the two intersect will determine where the image is formed. So altogether, when you do the ray tracing, these are the four light rays that can help you determine where the image is. Usually, you just need two light rays to determine, but sometimes it may not be that obvious. Then you might use additional one or two to determine where the image is formed. Okay. So so we discussed how the image are formed by a mirror. And image can also be formed by refracting surfaces. So this is something that when I say refracting, it means that when you have a light, when you have an object placed in front of the refracting material, and then the light, some of the light will be refracted through the it'll be refracted in inside the inside this object, and the image can be formed. Okay, and so so we're not going to dwell upon this, because we're going to focus more on a real ideal case when you're dealing with the thin lenses. This when you have the lens that have a substantial thickness, but so anyway, so suffice to say that the equation was subject to some modification, because now this actually comes with some sort of thickness. So there's an index of refraction that needs to be considered. So instead of 1 over P, now it's N1, which is the material where the object is, and 1 over P plus N2 over I, and N2 is this material, and that's equal to N2 minus N1 over R. And R refers to the curvature of this. So if you have, if you have a convex surface, so if this is a convex surface, your R is positive. If you have a concave surface, then your R is negative. Okay, so that's how you, how you determine. This is a little different from the, a little bit different from the mirror, because when you have a concave mirror, your F and R are positive. When you have a convex mirror, your F and R are negative. But when you're dealing with a refracting surface, for convex, that is positive. For concave, that is negative. Okay, and so this just for your information, and you can see that if we did everything, if this N1 and N2 are air, then you pretty much go back to this 1 over P1 plus 1 over I1, and that will be 1 over yeah. So similar to the lens equation, but when you're dealing with a refracting surface, then this is the equation to use. So as I mentioned, it is the thin lenses that we want to spend more time on. So let's say we have two different kinds of thin lenses. One is convergent lens, one is diversion lens. And why were we saying that convergent and diversion? Because the name itself is very, is very telling. When you have a convergent lens, it means that light ray will most likely converge. And when you have divergent lens, it means that light ray passing through divergent lens, the light ray will most likely be diverging. So you can see that this is a convergent lens that comes with the two surfaces. So this is the one. This is the first. This is if the object is on the left side, and then so the center curvature of this first surface. So this is C1. And for the second one, that is your C2. This is nomenclature, just so you know. And so that it comes with a radius. For each surface, it has a radius. So that's just for simplicity. We'll just say that R1 and R2, they are equal to each other. So their focal length is also will be the same in magnitudes. So how do we, so for thin lens equation, we again use this equation to calculate where the image is formed. So you have 1 over I plus 1 over P, that's equal to 1 over F. And F, being thin lenses, so F we'll just use one single F. Okay, so so let's see how the image is formed. You send a parallel light ray to to this lens, and so the lens light can go through this material. So it's going to be refracted, and it's going to refract it, toward the central axis. So you have one light ray that's get bent, and then you have another parallel light ray, and then it's going to get bent. Okay, so you can see that they converge at this point. And you can see that this is the real focal point, because real light ray converge at this point. However, when you're dealing with a diversion lens, you still send the parallel light ray to this surface, and then it's going to be refracted, And so that's one refracted ray. This is another refracted ray. You see that these two, they do not converge on this side. Instead, you have to draw the extension line, and they both converge at this point. So you can see that your F here is a virtual focal point, has a virtual focal length. So your F here is negative, your F here is positive. So when you have a convergent lens, your F is positive. When you have a divergent lens, your focal length is negative. And then here's another equation, which we call a lens maker's equation. This is the empirical equation for the lens maker. They will use this equation to determine the focal length of the lens, and that is 1 over F is equal to N, which is the index refraction of the material over the medium. The medium, it can be air, can be some other material, and minus 1, and then 1 over R1 minus 1 over R2. R1 is the radius of the first surface. R2 is the radius of the second surface. Okay, so if you look at this, we can just look at this, because so this n over n medium minus 1 is always positive. Let's look at the sign of 1 over R1 minus 1 over R2. So this is the convex surface of a lens. So then this R1 is positive, and this is a concave surface. So your concave surface. So your R2 is negative. So 1 over R1 minus 1 over R2. This being positive, this being negative. So negative become positive. So you know that your F here is positive. So for a convergent lens, your F is positive. Now let's look at the diversion lens. So this is a concave lens. So R1 is negative, and this is a convex surface. So your R2 is negative. So you have a negative here, a positive. So you have negative here, and then your R2 is positive. So negative, your F is negative. Okay, so this is the equation. The lens maker's equation is just something for you to know, but most likely we're just going to use this equation to calculate where the images is formed. Okay, so so here are additional examples to show you how the image are formed using the different kinds of lens. So let's say you have a convergent lens. You place the object that's inside the focal point, and let's see how the image are formed. So you send a parallel light ray, and the parallel light ray has to go through the focal point, okay, and it's bent toward the central axis. And then you have another one that goes through here, get bent, and then you can see that those two light rays will not converge on this side, instead converge on the other side. So you can see that the image here is an enlarged image, and it's a virtual because it's virtual light ray. And also, so your I is negative, and your M has to be positive because they have the same orientation, and your M is greater than 1 because it is an enlarged image. Okay, now let's look at when you place the object that's outside the focal point and see how the image is formed. So when you place an object that's outside the focal point and just follow the light ray, you can see that it is formed on the other side where the object is, because in order for light rays to emerge on the other side. So this image is real, and so meaning that your I is positive, and it's flipped because then your M has to be less than 0, and it's also enlarged. So your M is will be greater than 1. Okay, it has to be. So we can see that for real image formed by the lens, it has to be on the other side of the lens, and this is the virtual image, so it has to be on the same side where the object is. On the other hand, if you recall, for the mirror, real image has to be on the same side where the object is, because the light ray, mirror is a reflecting light ray, so it has to be on the same side where the object is, or in front of the mirror, in order for the light ray to converge. Now let's look at the diversion lens. For diversion lens, we follow the light ray, so you can diversion lens always produce a virtual image. So this is one light ray that's being diverged, another light ray that's being diverged, and then you draw the extension line, and and you see that this is where the object is. It is upright, same orientation. It is virtual, so I is negative, and it is smaller, so your M will be less than 1. Okay. And here, so previous example shows you how the image are formed, and you might say, okay, those, how do you draw the light ray? That seems to be very arbitrary. So now that's, that's doing, let's see how use this light ray to determine how image is formed. So just follow this basic principle. Parallel light ray will go through focal points. Light ray goes through focal point will be parallel after refracting off the surface, refracted through the material. And then when you have light ray that goes through the center of the lens, it will be no deviation. It will be there's no deviation. So these three light ray can help you determine where the image is formed. Okay, parallel focal point, parallel, no deviation if it's through the center of the lens. So and then they converge at this point. So you can see that this image is real, is up, is flipped, and on the other side where the object is. And so this is actually easy to do. But what if you have an object that's actually inside the focal point? Then it will be difficult a little bit difficult to draw. So again, follow the same principle. Let's see, for the first light ray, parallel has to go through the focal point, go through the center of the lens, no deviation. And then this one, if it's coming from the this focal point, then it will be parallel. And then you draw the, these three do not converge on this side. So you draw the extension, and extension. You see that it converges at this point. So it's a virtual image. Okay. Now for diversion lens, again, parallel focal point. So you'll be diverge. So you'll be actually away from the central axis. Parallel, diverge, and then through the center, no deviation. And then this one is when if it's parallel, it has to come from the focal point or something like that. So when you draw the extension line, you will find out this is where the image is formed. Okay, so those are the basic light ray that can help you find where the image is formed. Okay, so this describes how image is formed by each individual lens. What about now? I place like two lenses side by side and see where the final image is formed. So in this case, what you need to do is that you have the two lens system of let's say I have lens one. I have, I don't know, lens two. It can be virtual, or it can be a divergent convergent. That just say this one has f1 and this one has f2 focal length, and you have an object placed in front of the first lens. Okay, so this is your p1. So in other words, when you have two lens system, you want to apply lens equation twice, and you want to do it one treating the second lens as non-existent after you find the after you apply the lens equation to the first lens to find the image formed by the first lens. Then use that image I1 as the object distance for the second lens, and treat the first lens non-existent. Okay, so in other words, you have the P1 here. It's going to form, let's say, it's going to produce the image real, and maybe somewhere here. And because it's real, we know that has to be flipped. And then so this is your I1. As you can see, your I1 becomes the P2. Okay, so just by this diagram. So this is your P2, and then you apply the 1 over P2 plus 1 over I2, that's equal to 1 over F2. Then you can get your I2 to see where the final image is. Or you could have a situations that you apply 1 over F1, 1 over I1 plus 1 over P1, that's equal to 1 over F1 to calculate I1. And you find that your I1 is actually further down, is actually here. So let's say you produce the first image produced by the first lens is I1. So again, it is a real image. Okay, so it'll be somewhere here. But then what is your P2? Your P2 then will be this distance. So that will be your P2. In addition to that, because it is behind the lens, your P2 has to have a numerical value that's negative. Okay, Your I1, when you calculate I1, you will get this distance. That is your I1. Okay, so you have to know, just based on the numbers you're given, you have to deduce what is your P2. P2 is this distance. Okay, and it also comes with, and you have to put a negative sign, in front of it to indicate that it is behind the lens, and then apply the lens equations again to find your I2. Okay, or you could have a situations that you have the P1 here, and then you produce a virtual image. If it's a virtual image, let's say is produce a virtual image somewhere here. Okay, then so let's say this is your I1. Then you can see that your I1 and here that is your P2. So you need to know, you need to base on the numbers to see what is this distance. And this is being in front of it. So, it is positive, but you need to figure out based on your I1 here, maybe the separation of these two lenses, to determine your P2. So you can see that your P2, there's no fixed formula to determine P2. The only principle that you need to go by is that once you calculate I1, mark it on this two lens system to see where your I1 is. And then based on the diagram to determine what is your P2, okay? Once you have your P2, then you apply the lens equations again to find out your F2. So there are some exercise problems that you can do, and to kind of like apply the principle to make sure that you understand the image the process for image to be formed. Okay, so it's basically that. And what about the magnification? Because this being a two lens system, your magnification, you will use a combined one. So for the first lens, you will use M1, which is negative I1 over P1, and then you have your M2, which is negative I2 over P2, and then you calculate each individual M1 and M2, and then you multiply them together to get your total magnification of the two lens system. Okay, and remember, when you have when your M is negative, the image has to be flipped, and then you may flip once, you may flip twice for a two lens system. Okay, so it really depends on the size of the M1 or M2. So that is that. And then there are several applications for the lens. One that is used a lot is what we call the magnifying glass or magnifying lens. So let's say for healthy eye, when you're young, your eye will naturally focus at 25 centimeters. So this is our the focal length of our eye. So let's say you have an object placed, about the your focal point of your eye, and then you can see that clearly. So it's making an angle theta here, and this is the object height, and this is your natural focal length of your eye. So let's say when you get older, you can't see things clearly, so you want to use a magnifying lens to see it better. So we would place a magnifying lens in front of our eye, and then this object will produce an image that is enlarged and is virtual on the same side where the object is. And so then how much is being magnified? So we can use this equation. So this is called the angular magnification, which is the theta prime over theta. Okay, and how do we calculate your theta prime? Your theta prime is basically the object distance and then over the focal length of this lens. Okay, so it's h over f. Now, what about your theta? Your theta here will be the h over 25. So when you do the ratio, you'll find out the magnification will just be 25 over 25 over the focal length. Okay, so that's basically how you find the magnification of a simple magnifying lens. Just simply if you know the focal length of the IP of this, then you can calculate how much is being enlarged. And there are separate applications of the lenses. Now, the most commonly that you know is compound microscope. So what is the working principle for compound microscope? It consists of two lenses. One is called the objective, where you place an object, under the objective, and one is called the eyepiece. So the eyepiece, the working mechanism for the eyepiece is very similar to the magnifying glass and the objective. So you have this basically a two lens system. So you place an object in front of the objective, lens, and this being outside the focal point, so it's going to produce a real image. So if we follow a light ray, parallel focal point, parallel, and you're going to see that it's going to produce a image that is real, and it's real, and it's inverted, and it's close to the inside of the focal point of this eyepiece. So when you have an object that's placed inside the focal point, it's going to produce an enlarged and virtual image. So what you see here is that, following the light ray, you're going to see that the final image that you're going to see is actually inverted, enlarged, and is virtual because it's on the same side where the object is. So initially it's a real image, and then when it goes through the eyepiece, it becomes an enlarged image. And you can see that it's actually upside down. So that's why, when you use a compound microscope, the thing you see is actually a flit of the original object. So the magnification, because we're dealing with two lens system, the magnification is actually consists of the M, which is the this one, and the M here. Okay, so the M here would just be negative I over P. So that will be by approximation. The I would just be the tubes, the length of the tube, and the P here would just be the object, the focal length of the objective. Right, this is a approximation. So your M here is negative as of over the focal length of this one. And what about the this M? So the M theta here would just be the 25 over the focal length of the eyepiece. So altogether, this is how much the this object can be can be enlarged. That will be you can use this equation to estimate. So this is basically the working principle for compound microscope. Another application is the telescope. So microscope is the one that we want to see a very small object. So we enlarge it to such a extent that we can see the details of that tiny object. Now, when you are using the two lens system as a telescope, the goal is to actually see a distant object and bring it to you in front of you. Okay, so it's a little bit different, and let's see how how they work. So this is what we call the refracting telescope. Also consists of two lenses. So we have this called objective, and this is called eyepiece. So remember, the object is so far away. We'll usually use the telescope to observe a star, a planet. So they are so far away. Light rays is coming. Your object, is coming from very far away distance. So parallel light ray coming through this through the first lens, and it's going to converge at the focal point, and then that focal point is that's going to coincide with the focal point of the eyepiece. So you have the it is a so the first image produced by the first lens is located at this point. That is that is the object for the second lens, and this object being at the focal point of that is going to produce an image that is so far away, almost close to infinity, and it's going to be and so that you can actually see here. Okay, so that's basically how how it works for use the two lens system to observe distance objects. And the magnification, so for the magnification, basically it follows this simple simple equation that will be the ratio of the objective over the focal length of the objective to the focal length of the eyepiece. Okay, so so this is basically how it works. So this is refracting, refracting telescope. There's also a reflecting, telescope as well. So it comes with a different design, but it's always utilize the same principle to to produce an image that you can see, bring the distance object to closer to you that you can see. Okay. All right. So the next few pages are just you can just ignore that. Those are just the equations describe the how yeah, you don't have to worry about that. Okay, so so you'll be just up to optical instruments. Okay.